Hello everyone. With what we learned in the past 2 lectures about capacitors, I guess we're ready to start doing circuit analysis for circuits that include capacitors. At this point, for this level, for this course, we're going to limit ourselves to circuits in which the differential equation that we have to solve for the math component of the analysis is going to be a first order differential equation. And the solution to that first order differential equation for a general form like this, where you have dy dt plus yt over tau, a constant, is equal to a constant, is given in this form. It's an exponential equation in which y infinity is the final value of the function, y0 is the initial value of the function, and tau, it's called the time constant. We explain why it's called a time constant, but generally speaking, once you bring that basically do the math and write the differential equation for the circuit, then this in this form, then this constant ends up having a unit of time, and that's why it's a time constant. So let's start doing analysis for a simple circuit. In the same lecture, I'm going to then, after finishing this simple circuit, I'm going to do another one for a relatively more complicated one, and that should conclude our discussion on circuit analysis with capacitors, and you can do a lot more homeworks after that using the same simple technique that we're going to explain. Okay, so this is the circuit. Now, you notice that there's a component in this circuit that we haven't discussed in the past. Well, we know about the current sources, and the equation that defines current source is basically the equation for it is that the current that is passing through the current source is equal to a value given. We know resistors, and we know the equation that defines the physics of the resistors. Now we do know capacitors and the equation that defines the capacitor. The new component is this switch. It's called a switch. What it does is that at a certain amount of time, in this case, t equal to 0, the initial time for the analysis, this switch turns on and connects the capacitor to the right to what's to the left of the circuit. So this circuit before t equal to 0 is not connected to the capacitor, and after that it gets connected. That's the only new thing that we have there. So this shows, the direction of this arrow shows that this switch is going to be closed at t equal to 0. If the direction was going the other way around, it would tell you that the same at same t equal to 0, the switch is going to open up. So this makes connection at t equal to 0. The other way around, it would disconnect at t equal to 0. Okay, so with that assumption, we're going to do a circuit analysis. Now, we already explained that the circuit analysis, the rules of the game is the same 3-step analysis, and the algorithm doesn't matter what components in the circuit. So what we're going to do is to first identify the nodes in the circuit. So there's this node, and there's now, before I move on, I want to explain to you that there obviously, because this circuit does have that switch, there are actually 2 different circuits that you have to analyze. There's one circuit before the switch, and there's one circuit after the switch. So before the switch, this is a node, and it's disconnected from the other side, right? So let's start with that, and then move on to the next stage when you have to basically assume that the switch is connected. So t is less than 0. This is the circuit that you're dealing with. The other end, the capacitor, is basically open, and there's nothing happening in the capacitor, obviously, because it's not connected to anything. So any action in this circuit before t equal to 0 is on the left-hand side, and the circuit is relatively simple. So for that simple circuit, I'm going to assume that this is my ground, and I call that node my V1, or yeah, V1. Now, I'm going to call that V1T to be consistent with later on calling the whole thing V1T. And we said as soon as we have capacitors, we're going to call everything V1, a function of time. So now I know that. Then this is IS, obviously, that current, and writing KCL for that node, this is now going to be IS2. So I already wrote KCL for that node. So with that, the circuit becomes really simple to analyze. There's no KCL to write. I already did that by calling this IS. And so the equation for this component is already written. There's only one component for which I need to write the equation for, and that's the resistor. So IS is equal to V1T minus 0 over R. So in other words, V1T is equal to RIS. And that's it. So I have the IS is known, and based on that, now I know the current in a circuit for both components is IS, and the voltage up there is R times IS. This shouldn't surprise you. It's a simple Ohm law for the resistor. Now, the good thing about this is that this analysis now tells me that V10 minus is equal to RIS. What do I mean by 0 minus? I mean right before the switch turns on, or right before the switch closes, the value of that voltage, V1, is RIS. That's what I mean. Okay? So this is important because this is going to help me solve that differential equation. Is going to help me basically know what the initial value for that the differential equation is. Keep that in mind. We move on to the second stage of the analysis, where now the switch is closed. So T greater or equal to 0. So now, after the switch, I can extend this node to include the top of the capacitor. Now I'm going to call this VCT, because it's the voltage of the capacitor, basically. So that node I'm going to call VCT. At the same time, I notice that this current is no longer equal to IS. I'm going to call that IRT, and the current passing through the capacitor, I'm going to call that ICT. Now I start writing the equations. So now I do have a KCL to write. KCL says the IS going into the node VCT is equal to IRT plus ICT. And then equations for components. There are 3 components. The equation for that one is already written. There are 2 components to write the equation for. First one, IRT, is equal to VCT minus 0 over R, and ICT is equal to capacitance D, derivative of the voltage across the capacitor, which in this case is VCT minus 0, or VCT over dt. And that's it. Now I'm ready to solve this set of equations. So for that, I simply take these 2 current values, put them in that equation, pretty much the same thing that I would do if these were just resistors. So with that, I have C d VCT dt plus VCT over R equal to IS. Now, if you notice, in this equation, there's only one unknown. It's the VCT. And this is a differential, first order differential equation. All I need to do in order to be able to use that solution for it is to bring it to the same format, and I'm ready to use that general solution. So for that, I'm going to need to divide, assuming that my yt is VCT, I just need to divide both sides of this equation C. So I get dVCT dt plus VCT over RC is equal to IS over C. And done. And in this equation now, if you notice, yt is my VCT, RC is the tau, and this is the k in that equation. Okay, so therefore the general solution for this would be VCT is equal to VC infinity plus VC0 minus VC infinity times E minus T over RC. And that's it. Now I have the voltage of that node. The only thing that is missing is to know what VC infinity and VC zeros are, and I'm done. So let's do that. What's VC0? The voltage of the capacitor right before the switch. Let's say it's a number, whatever that is. It could be 0, it could be anything. So let's say VC right before the switch. So 0 minus is right before the switch. Let's say that's V0, something, a constant. Could be 0. And that's a given. Now, this VC, mathematically speaking, could be different than that because this is VC 0 minus. Now, this equation is going to put a limit on how the voltage of a capacitor can behave. Why are we saying that? Because the current that is passing through the capacitor is derivative of the voltage. So if the voltage of the capacitor changes abruptly, mathematically speaking, derivative of a function that changes abruptly is infinity, which means that the current that is passing through the capacitor would become infinity, and that's physically impossible. So with this in mind, we can conclude that the voltage of a cross capacitor cannot change abruptly. So going from 0 minus to 0 plus, the voltage has to be continuous and has to be, in other words, equal because they're really close to each other, right? In other words, if VC minus is V0, then VC0 is V0. And that takes care of the initial value of the capacitance for me. So it's a given. Whatever that is, I'll put it in there. Now, how about VC infinity? Now, since this is an exponential equation, right? Basically the value here, or in other words, in this circuit, if you notice, if we just let time pass, what happens, we know, is that charge is going to start accumulating across the capacitor, and as the charge accumulates across the capacitor, the voltage is going to rise, but then when the voltage rises, then there's going to be the current that is going into the capacitor is going to start reducing, and then this process eventually is going to saturate and become stable. In other words, that's why the solution is an exponential function. So with that in mind, if you wait for infinite amount of time, the voltage across the capacitor, or voltage in this circuit, is going to become something constant, and the current that is passing through the capacitor is going to be infinity. In other words, you cannot have a current passing through the capacitor in the same direction for infinite amount of time. Why? Because even if that's a small current, if there's some current, that means that the voltage is going to keep increasing, right? As the more charge goes in, the voltage keeps increasing. And obviously, in a circuit, there's a limit in what the voltages in the circuits are. So in other words, the voltage across the capacitor has to saturate. So therefore, the current that is passing through the capacitor has to, at some point, become 0 or really close to 0. At which point the voltage, it just becomes constant. Now, if the voltage for time infinity becomes constant, then this equation is going to predict the same thing. It's going to say if the voltage is constant, then the derivative of a constant function is 0, right? In other words, from this equation, I can actually calculate what VC infinity is. If I know that VC infinity is very much like a constant function, then dVc infinity dt goes away, so that term completely goes away. So from this, I know that Vc infinity is actually equal to IS, which in other words is the same thing as V10 minus. Let's put this here first, and then we go back to kind of making sense of what happened right there. So now I know VC infinity. I already know VC 0. I'll put them both here. So VCT is equal to VC infinity, which is RIS, plus VC 0, which is V0, minus VC infinity RIS, e to the minus t over RC. And this is it. Now I have the voltage of that node. I can put it back here, calculate the current of the resistor. I can put it back here and calculate the current of the capacitor. So I have calculated all the voltage and capacitor in the circuit, and I'm pretty much done. Now, why are these two intuitively equal to each other? Because this apparently came directly from the fact that we kind of concluded that the voltage across the capacitor, when you wait long enough, becomes a constant, and therefore this term in the differential equation goes away, right? But if you notice, if this voltage becomes constant, or in other words, if this current becomes 0, it's the same thing as saying that this part of the circuit is no longer really doing anything in the circuit. If this current is 0, it's the same thing as saying this switch is open, right? So when the source is connected into a RC circuit are constant, and you wait long enough, t equal to infinity, the capacitors could be considered as open circuits. There's no current passing through, which then brings us back to what we calculated before the switch, right? So the voltage becomes the same thing as we calculated there. Okay, so how does this equation look like? Let's say if the V0 was 0, then you have RIS times 1 minus e to the t over RC. So the voltage is going to go up and then saturate to the value of RIS. That's so it's going to look over time. The voltage is going to look like this, voltage VC. And this is this value right here is RIS. So it starts at 0 and then quickly goes up and then saturates, and the saturation value is equal to RIS. Now if you put t equal to 0 in this equation, you can see at t equal to 0, that's equal to 1. Assuming that's 0, that becomes RIS minus RIS, that's 0. At t equal to infinity, this whole term is 0, so this whole term becomes 0, and you end up having RIS, which kind of predicts the initial value and the final value that we are showing in that. So an exponential increase and then saturation, a quick saturation at the final value, because it's an exponential equation. Okay, so with that, now we're ready to move on to a relatively more complicated circuit. I'm going to stop and then come back. Okay, so now this is the second circuit that we're going to analyze. Obviously, it's a bit more complicated than the one that we already did, but our approach is going to be exactly the same. We're going to label the circuit, and again, there's a switch in the circuit. The switch changes position at t equal to 0. So before t equal to 0, it connects this capacitor to the circuit to the left, my left, and when it switches to the other side at t equal to 0, the same capacitor gets connected to the circuit to the right. Now, with that, therefore, you have to do the analysis twice. Now, the question is going to tell you that this switch, before t equal to 0, has been in this position for a very long time. And that matters because when the question says something like that, you know that in this circuit, since the voltage connected to the circuit is a constant value, over time this capacitor is going to charge up and the current is going to go down to 0. Okay, so in other words, when you're doing a calculation for before the switch, which I'm going to do right now, t less than 0, you can assume that this capacitor is not drawing any current. In other words, you can treat that like an open circuit, at which point the circuit becomes really simple to analyze. So that voltage right there is 40 volts, and this voltage right here, let's call it VCT, right? Before the switch, that VCT is basically just the voltage divider, simple voltage divider. So you can just label the circuit, write the equation, and get the same result, but you can quickly, from this, conclude that VC0 minus is equal to 40 volts times 60, assuming that that's our ground, over 80, 60 plus 20, which is the same as saying this is 30 volts. So right before the switch, the voltage of the capacitor is equal to 30 volts. Now, if you remember, because the voltage of the capacitor cannot abruptly change, therefore from this I can quickly conclude that C0 is equal to 30 volts, which is right after the switch when you move to the other side, or 0 plus for that matter. Same, 0 minus, 0 plus, 0, they're all the same voltage because the voltage across the capacitor cannot abruptly change. So now I do the switch, and so really circuit analysis for that part was really simple. And I analyzed this new circuit. We no longer really care about what's to the left, but what's to the left we've already done actually. So there's nothing much to be done there. From this voltage you can calculate the currents that are passing through these two resistors if they're important for you. For example, the voltage, the current here would be 40 minus 30 divided by 20 milliamp, and the current here would be 30 minus 0 divided by 60 milliamp, and they have to be the same obviously, and they are. Okay, so now let's move on to t greater or equal to 0. So I'm going to start labeling this again. We still use the same node voltage VCT for that one. I'm going to call that V1. And now here I can write the equation for this component. This voltage minus that voltage is 75. So that voltage is actually minus 75. So be careful when you're labeling this one. It's not 75. Notice that how we define again. Make sure I didn't do it wrong. This voltage minus that voltage is 75. And that's 0. So 0 minus that voltage is 75. So this voltage is minus 75 volts. Okay? So I have labeled all the nodes. Now the currents, I'm going to call this ICT for that node. KCL tells me that that's ICT. I'm going to call this I1T. Let's call this I2T. And this would be the same I2T. KCL for that node. And that's V1T, right? So we're ready to write KCL for that node. Okay, so now KCL for this node. ICT goes into that node, and I1T and I2T are leaving. Equations for component. We have 1, 2, 3, 4, 5. That one's taken care of, so 4 equations. Start with the resistors and then finally with the capacitor. So ICT, this current, is equal to VCT minus V1T divided by 8K. I1T is equal to V1T minus 0 divided by 160K. And I2T is equal to V1T minus 75 divided by 40K. And finally, for the capacitor, ICT is equal to the capacitance 0.25 times the derivative of the voltage across, which is that voltage minus this voltage, or in other words, 0 minus VCT. So 0 minus VCT dt. And that concludes the equations that we have to write. Now, we have to manipulate these equations. We have 1, 2, 3, 4, and 5 unknowns, and 5 equations. So we should be able to solve this set of equations. I'm going to have to manipulate it to turn it into one equation with one unknown and then work backward. So here's how I would do it. If you have a good calculator, all you need to do is to input this set of equations, and then the calculator is going to spit out everything, including solving the differential equation for you. But let's try to do it at least once with hand. And take that and put the values for the current and IC from these equations. So from that I have minus 0.25 dVCT dt equal to V1T over 160K plus V1T plus 75 over 40K. Then I can take these two and equate them to each other. So VCT minus V1T over 8K, that is equal to this. It's also equal to minus 0.25. In other words, I can equate that to these two. That might be easier to do. It's equal to V1T over 160K plus V1T plus 75 over 40K. Good. Now, with this, I got rid of all the current unknowns. I only have 2 unknowns and 2 equations, much closer to where I need to be. So I can multiply both sides of these equations by 160K. That would give me 20K times VCT minus V1T is equal to V1T plus 4, sorry, this was 20. 4 times V1T plus 75. With this, I can manipulate this, move it around. So 20 VCT is equal to 20 V1, that's 5, 25 V1T plus 300. So with that, I can figure out what V1t as a function of Vc is and put it in that equation, and I'm all done. So from this, I have V1t is equal to 20 divided by 25 Vct, which is 4/5 Vct minus 300 divided by 25, which is 12. I'm not mistaken. Minus 12. Yes. So now I can put that back into that equation, and I get one equation. I put this V1 back into this equation, and I get one equation that is only a function of Vct. It's a differential equation that is only a function of Vct. So let's first multiply both sides of this equation by 160k. So that's 160. This is minus 0.25 times 10 to the minus 6, right? That's microfarad. So 160 times 0.25, that's minus 40 times 10 to the minus 3. dVct dt, and the other side is equal to V1t plus 4V1t plus 300. There you go. And now I have 5V1t plus 300, so that multiplied by 5. So the final answer would be 4 times 10 to the minus 2 dVct dt is equal to, now 5 times this, that would be 4 Vct minus 60 5 times this plus 300. Which that is 240. This is plus 240. So now moving things around, I don't have enough room, so I am going to just move the same thing around and divide it and rewrite it on the same line. So that would be dVc dt. I want to turn it into that form. Divide both sides by 4 times 10 to the minus 4 times to the so that would be d plus Vct over 10 to the minus 2, and this would be minus 60 over 10 to the minus 2. That should be the differential equation that we are looking for. In other words, it's equal to minus 60 over 10 to the minus 2. That's it. This is the differential equation. That's in that form. Now I can solve this differential equation. Now, what's the initial value of V0? I already have it. What's tau? It's 10 to the minus 2. What's the final value? The final value, that goes away. Vc infinity is this times that, which is minus 60. So you put that there and you get VCT. I'm going to try to fit that somewhere here so that you have the final answer to check later on. So VCT would be V infinity, which we just said is minus 60, plus V infinity, which was minus V0, which was 30, minus 60, which is plus 60, times e to the minus 100 t. T divided by 0.01, which is minus. So minus 60 plus 90 e to the minus 100 t is your answer. And we're done. Notice, the math was relatively lengthy, but the approach is the same. If you know the differential equation solution, it takes some time, but it's not impossible to do with hand. There are ways to simplify the math by using some tricks and changing the circuit, but this is the most comprehensive way of doing it that gives you everything that you're looking for. Now, once you have VCT, you can put it back into any of these equations and calculate any of the, for example, from VCT, we already have this equation. You put VCT in this equation, you get V1t immediately, right? And then you have V1t, you put it in that equation, you get I1t, you put it in this equation, you get I2t. So with this, you quickly get everything once you have solved that differential equation. I hope this turned out to be a relatively long lecture, but that concludes everything that you need to know to be able to analyze circuits with capacitors. Thank you.